Margaret. Here we go. Now, I would highly recommend that you write this down, okay? Everybody's got this balanced? What type of reaction are we looking at here? This thing, as I told you, this page right here is very similar to the Chapter 8 problems. Hopefully I don't need to say any more about that. I recorded that I said it, so you can't deny it. You've been warned, all right? What type of reaction are we looking at here, Mr. Mallard? I don't know what it is. I don't know what you call it. I think it'd be kind of like a decomposition type thing. That's what I'm saying. When you look at these reactions, it's not always cut and dried as you'd like to think, you know, from your textbook. But what we have is this iron 2. Well, you know the name of this. What is it? Negative. I misspoke. Go ahead. Think about it again. It is in a form of iron oxide, but iron's a transition metal, so you got to put the Roman numeral. What's the charge on this iron atom? Think again.
Oh.
It's iron 3 all day long. Now, you should be beyond that stage, okay? I mean, you look like a guy who tries to 101A in chemistry, okay? Okay, you should be beyond that by now, all right? The low-level thinking is you would just take this subscript right here and stick it back up there as the charge, right? But the way you really look at it is each oxygen is 2 negatives, so you got a total of 6 negative up here. So you must have a total of 6 positive, and you only have 2 irons. So this is iron 3 oxide, and by the way, this is common rust. Okay, this is the common rust, okay? So now how do you balance this thing? Well, it truly is trial and error, and the more you try, the better you get at it. But you got the 2 irons here, and you start with this single element over here. And so just try the 2 right there and see what that does for you, okay? You've got the three oxygens here, so you try 3 here, that'll balance out your oxygen. So now your irons and your oxides are balanced out, right? You've got 2 irons here, 2 here, 3 here, 3 here. What does that do for your oxygens? Well, as it turns out, boom, and that works, right? Okay? And it is that easy sometimes. It's not always, but sometimes it is, okay? So here we have solid aluminum. And I don't really, I should be more of a stickler about it, but I'm not, about putting these states on these things, on these type of reactions where it's not, this is not the critical issue what the state is, but this is the way you would write it, okay? And so when aluminum and nitride, IDE, meaning it is a element, right? The ion is an element. When aluminum and nitride bond, what is the relationship, what is the ratio? We know we're going to have aluminum and nitrogen. What is the ratio? This doesn't look like a February class of chemistry students. The aluminum's always 3+. The nitride ion is always 3 negative, so it's a 1-to-1 ratio. So the only issue in balancing it then is this 2. This is nitrogen's a diatomic gas. They told you deliberately that nitrogen was a gas. It's diatomic. That should have been the only issue for you to consider, right? This is diatomic, so you have to write it as N2. That forces a 2 there, and that 2 forces a 2 there, okay? Now, folks, if you don't ever work these, if you don't ever practice these, I don't expect, and you shouldn't expect to get very good at it, okay? Like shooting basketball or anything else, okay? Wishing and hoping. Well, it's better than nothing, but it's not what it is, okay? You have to practice these things, okay? Now, types of chemical reactions, we've been through this 100 times. The first one your book mentions is what? Synthesis. What else could you call that? Combination. I don't know. I can't even remember from textbook to textbook what they call them. But synthesis, combination is the same thing. 2, the opposite of that would be decomposition. Okay? Then we have single displacement. And how can you tell when you're looking at a single displacement reaction? I mean, what's the easiest, the most obvious thing? If you have one metal, it's almost always when they're testing you in this scenario, you're going to have one metal added to a solution. And the issue is what? If that metal is higher than the cation in solution on the activity series, it's going to displace it. If it's lower, what happens? Nothing. Okay. Fourth type of reaction then is double displacement. And what has to have happened before we can have a double displacement reaction? There's three things. I'll put a three out here. 1, 2, 3. You have to either have a insoluble salt, which would be another term for that would be a precipitate, right? If it's an insoluble salt, it's going to precipitate out, okay? So you have an insoluble salt, a gas, or a molecule, and molecules always water, and that type of double displacement would be usually acid-base, or neutralization, right? And the point is this, is that a pair, in the double displacement reaction, you have two pairs of ions. And potentially, they're going to switch places. If they do, that's a double displacement reaction, okay? But the key is, one pair has to be removed. Otherwise, nothing changes, right? If you have four ions, two sets of ions, and they're soluble in water when you start the reaction, and you finish the reaction, you got the same four ions, and they're soluble in water, nothing happens. So there's two of them have to be removed. One pair of them has to be removed. And the most common in this testing scenario here in beginning chemistry is they're going to show you insoluble salt. What is a salt? Ionic compound. What's ionic compound, right? Cation, anion. They're going to precipitate out of the solution and leave you the remaining two. That's the double displacement. Now, number 5 here is combustion, okay? Combustion, I tend to focus on, and maybe too much, on like this one right here where we have combustion of a organic compound, a hydrocarbon. And the key there is the products are always CO2 and water. But if it's not a hydrocarbon, no water. It may not be CO, right? It may not be a carbon oxide, carbon monoxide, carbon dioxide, whatever, right? So what, like in the lab we did the other day, we burned some what? We burned that candle wax, C25H52, and we got CO2 and water, right? But we burned the magnesium, what did we get? Product. Magnesium oxide, MgO. There's no CO2 and there's no water in that, okay? So you need to check out your book there on the combustion reaction. Seems like one of the more simple ones because most of you are focusing on finding that CO2 and water in the product. And I hope that's what you see on the state test. But it may not be, okay? For instance, iron filings are extremely flammable. There's a danger warning on them. But you're not the least bit worried about an iron nail igniting, are you? I'm not, okay? But under the right conditions, it's like that's another matter of surface area. Okay, it's like that's why most chemical reactions take place in solutions because the water takes the ionic compound apart and exposes the ions themselves, and so then the ions are able to act and interact and so on. Okay. But anyway, this reaction down here, number 4. Benzene, so what do we have here? What type of reaction are we looking at there? Combustion. How do you know? CO2 and water, we got a hydrocarbon there, right? So how are we going to balance this thing? C6H6, and we're going to add oxygen to it, and whenever you're balancing these reactions with oxygen on the reactant side, leave that oxygen until the very last, okay? So CO2 and water. All right. So we'll just take a shot in the dark here and say we got 6 carbons. So let's put 6 carbons. We got 6 hydrogens. So let's put a 3 there. Give us 6 hydrogens. And now we look at it and we say it's not going to work. This is going to leave us with an odd number of oxygens, and no matter what we do over here, we're going to have an even number. Okay. So what's the smallest step you can take to get an even number? Double it, right? Double it. So now that gives us the 2 benzenes, right? The 12 carbons balance with the 12 carbons here. The 12 hydrogens balance with the 12 hydrogens here. And now we have a total of 24 and 6 is 30 oxygens. So it's a simple case of just putting 15 in, okay? Now, you want to do one last check and make sure that's the lowest whole number ratio you can have. And I believe it is. Okay, any questions about that? Yes.
How would you do the ratio? I guess 0.5 is the lowest number.
Well, yeah, what I'm saying is you cannot, there's no number that these four numbers can be divided in equally. Because of the 15, right? Alright, number 6, okay? This is an interesting little potential equation. Theoretically, this lead could go in here and displace the magnesium. That's what you might be thinking. The untrained eye might say, oh yeah, this is going to be a single displacement reaction. We're adding a metal to a ionic compound that's dissolved in water. But what's the deal? You look on page 286 and what do you find? You find the activity series, and what does it tell you? Right, it tells you that lead is below magnesium, and therefore, you're not going to have a reaction. The lead cannot displace the magnesium, okay? Now, you should know that, or have a good idea that magnesium is a group 2 metal, alkaline metal, fairly reactive, right? And lead is over there, one of those other metals, right? So when you look at it and you think about it in terms of the position on the table, the magnesium, you know, in our general terms, it's got a much lower ionization energy, which means it's more reactive than the lead, right? And you look in the activity series to confirm it, and you find out that's true, okay? All right, so now we're looking at this one, number 7, and this is potentially what kind of reaction? If we're going to have a reaction, what is this baby going to be? You got 2 salts in aqueous solution. So if it's going to react, what is it going to be? What kind of reaction is it going to be? Double displacement. So what do we have to have before we're going to have a double displacement? Huh?
Insoluble salt.
An insoluble salt is what we're looking for. And how are you going to find out if you have an insoluble salt? Not the activity series. Solubility tables or the solubility rules, okay? And you go to the solubility rules and you find out something, I hope. But anyway, let's balance it first. We got 3, again, this is trial and error. Look, you got 3 sodiums, and here you have 1 sodium. So stick your 3 right there, okay? Now you got 3 sodiums and 3 sodiums. You got 1 phosphate and 1 phosphate. 1 iron and 1 iron. You got 3 chlorides and 3 chlorides. Does that work? Is that all there is to it? Does it balance it? Yes? Okay. Now, when you look at the solubility table, what do you find out? You find out that lead phosphate is not soluble in water, or very slightly soluble in water. So that means here you do have a double displacement reaction. Okay? If the lead phosphate was soluble in water, in other words, if the lead phosphate did not precipitate out, then you would have no reaction. Okay? Questions about that? All right, so now we look at number 8. We're looking at, what's the name of this thing right here? What's the name of this lead compound? All right, Mr. Steve? Okay. Oh, did I skip it? Sorry. Let's finish 8 while we're on it, okay? What's the name of this lead compound? Everybody agree with that? He says lead acetate. Everybody agree with that? I hope somebody's going to disagree with it. Lead 2 acetate. Lead is one of what we call one of those other metals. Lead and tin right above it, and they can form two different ions. Each of them can form two different ions, a 2+ or a 4+. Okay, so you have to designate it with lead. It's really an exception. And so, if this reaction takes place, if this is double displacement, we're going to end up with lead 2 chloride and lithium acetate. Okay. And then we got to check the solubility tables. But let's balance it first. We have one lead and one lead, 2 acetates, so that'll force a 2 there. That gives us 2 lithiums, which will force a 2 there, and that balances out our chlorides there. Okay. We look it up in the solubility table, and what we have then is a insoluble product. So this is double displacement. And this is about the 4th or 5th time we've done this lead chloride thing. So you should be starting to pick up on that. Hopefully, on your state test, they'll give you lead chloride will be one of your products, and you'll recognize it from past practice. Right? Now, I think this thing is going to ask us to write the, yeah, it is going to ask us to write the total and the net ionic equation for that reaction. I wish I had it on the same page, but what we're going to end up with, I'll just rewrite it real quick. Lead 2 acetate. It doesn't hurt you to write these things over. You know, it's not like it's anything but practice, and practice is good. Some folks don't think they need to practice because they feel like they understand it, so that's it. But there is a huge practice factor involved in chemistry, okay? And all of these are aqueous, okay? Aqueous, okay? Now we balance them, and we have a 2 here and a 2 here. Now, what does aqueous mean? Very important. This little symbol right here that seems innocuous and might slip by some of you, don't let it. What it means is that these things are not, they don't exist bonded together. The motion of the water molecules, the Brownian motion, and the fact that the water molecules are polar, that's the critical issue. The fact that it's polar, it actually dissociates this substance into its ions, okay? And that's what allows this reaction to take place, okay? So what we have then is not the lead bonded to the acetate, is we have a lead 2 ion and 2 acetate ions, okay? And technically you should write that AQ here as well, okay? But I'm going to assume that you understand that, all right? Because I'm running out of space and my pen is kind of blurred, okay? So that gives us here, we have 2 lithium ions and we have 2 chloride ions, okay? And then at the end, when the reaction's over, we end up, when we got in our solution, we have 2 lithium ions, and now we have the 2 acetate ions floating around here, and we have the lead chloride, lead 2 chloride, and it is insoluble, okay? So this is what we would call the total ionic equation. The net ionic equation, all we're going to do is look on both sides of the reaction arrow here and cancel the ions we see on both sides, okay? And in this case, we see 2 acetate ions and 2 acetate ions, 2 lithium ions and 2 lithium ions. Now what this does, this is a fairly straightforward reaction, so it doesn't seem too critical. It seems almost unnecessary. But in some of these reactions that get more complicated, this will show you exactly what occurred. And if you've never practiced doing it on these straightforward ones, then you'll have a serious problem with the more complicated ones. So you want to practice going through these. What this tells you then is that you have lead 2 ions combining with 2 chloride ions, and you're going to produce the insoluble salt, lead 2 chloride. Okie dokie? Questions? No. Alright, now, mess up my video, but I gotta go back to 6 here. And 6, you should be familiar with this one. This was just in Anybody remembers that we put zinc and copper 2 sulfate in the lab? Well, what happened? We put solid zinc, we dropped that zinc pellet into that bluish copper 2 sulfate in aqueous solution, and again, that's the key. It means that you had copper 2 ions in the solution and you had sulfate ions in the solution. And so the question is, what type of reaction could this be? We're looking at a potential single displacement reaction. What does it rest on? What's the key? The key is page 286 in your textbook, the activity series of metals. Now somebody tell me, what is the key? What are we looking at on the activity series? Folks are boring. You're looking to see if zinc is listed as more reactive than copper or less, right? If it's above zinc on the activity series, then it's going to displace the copper. And remember that this AQ means that we have copper 2 ions and we have sulfate ions. If this thing were not dissociated, you wouldn't have any reaction regardless. Okay, but the fact that it's dissociated, now the zinc and the copper, right, can change their ionic position. In other words, the zinc can give up 2 electrons to the copper loses its charge and therefore cannot stay in solution. So what we end up with then is zinc sulfate. Now zinc, you don't say zinc 2 sulfate because zinc is always 2+. Okay? It's an exception, just like the one we did before there was the lead. Lead's an exception in the other way. You do use a Roman numeral for tin and lead, even though they're not in the transition block, right? Not in the D block. But in zinc, you don't use a Roman numeral, even though it is in the transition block. Okay? Those are all just little details that you got to remember. And what about the copper ions, the copper 2 ions we had floating around? They picked up 2 electrons, lost their charge, in other words, became 0 charge, neutral, and what happened to them? Boom, they fell out like a rock. Right? Questions? And what I'm telling you is if you'll work along with me and practice on these, and instead of making efforts not to listen and try to make sense out of this, you're going to run into these things on your test, and hopefully on that standardized test it's going to be very important to you. You'll run into some of these very same equations, but they're all, once you start to practice with them, they're all very similar. Okay? So here we're going to write a double displacement equation showing that it already telling you, it's already given up its hand. So when it says a double displacement reaction, and we got two salts in solution, what does it tell you about the product? It tells you one of them's insoluble. It's already shown its hand, right? Double displacement. So you know you're going to have an insoluble salt, right? And if you get that on that standardized test, that SOL standardized test, that's a big hint, right? A big hint. You want to make sure you don't miss that, okay? So it says calcium chloride. What's the formula for calcium chloride? Cl2, because the calcium we know is 2+. And we're going to bond that with, we're going to react it with lead 2 nitrate. So that means the lead has what charge? 2+. Nitrate is 1 negative, so we need 2 nitrates. Everybody understand that? Okay? Again. I'm lazy like this. You want to write those states in there, okay? Particularly when you're supposed to be learning about double displacement reactions, it's critical that you write those states there, okay? So now, we know that this is going to be a double displacement reaction because they already told us, so we're going to end up with calcium nitrate, again a 2+ and a 1 negative, so it's going to be 2-to-1 ratio, and we're going to end up with lead 2 chloride. Shoot, we just did that, right? Now, here you're going to look in your, I think this is page 860, it's appendix in 860, and that's the solubility table. okay? So you look at those solubility tables. On your test, they'll probably give you that somewhere in the region where they're gonna start asking this question. When you see them giving you solubility tables or solubility rules, your ears should perk up and say, ooh, I bet I'm gonna be asking about a double displacement reaction soon. So you look these up and you see that the calcium nitrate is aqueous and the lead 2 chloride is solid, okay? Now, again, this is a fairly straightforward reaction, so it's not too critical. This total ionic equation is not real revealing to you. But it's practice, it's good practice for the future when you get into some more difficult ones, okay? So what this AQ is telling you is that you don't have calcium bonded to chlorides, you've got calcium ions and chloride ions, and you have lead 2 ions, and you have nitrate ions. Everybody understand that? That's a huge difference. If you had these two things sitting as a pile of salt and mixed them up with a stick, you wouldn't get a reaction. But once you dissolve them in water, you're going to get the reaction, okay? So what happens is we're going to have a switcheroo here, and the calcium is going to hook up with the nitrate. And how would you know? Because they remain soluble, right? They remain in aqueous solution. And the lead, I'm messing up. This is total ionic equation. You're distracted, that's what happens. So the calcium ions here, and the 2 nitrates stay here, but the lead and the chloride ions form this insoluble solute. Insoluble precipitate. Insoluble salt. Got it? So when you write the net ionic equation, all you're doing is cancel the ions you see on both sides of the reaction arrow. There's the reaction arrow, okay? And you see calcium ions here, and you see calciums on the product side, so you cancel them. You see nitrates, 2 nitrates on the reacting side, 2 nitrates on the product side, you cancel. Here you've got chloride ions and lead ions. Here you do not, right? They are not ions over here anymore, okay? So that is the key to what happened in this reaction. That tells you the whole story. The lead ions hooked up with the chloride ions and produced the insoluble lead 2 chloride. Now you notice I switched that around. And that's just, I don't know if there's a rule about that, but you know, in the name, the least electronegative element is always first, okay? And so I always switch it around and put that cation in front of the anion no matter what, okay? I also, if I can, try to make sure I put this insoluble salt at the end of the reaction. You gotta be careful, okay? It may not always be the case. Okay, any questions on this? Anybody have any questions? All right, say it again. All right. Plan on seeing that again.